radar, and the afternoon will be devoted to interferometric applications, roughly speaking. Just a few quick notes. You're welcome to ask questions anytime. I'm here for you to help you learn this material. So don't sit there and if you're stuck on something, hope that it will just go away. Just ask the question. There's another 30 people in the room that probably have the same question anyway. So feel free to do that. I will skip over some of the detailed derivations, but they're in the notes. And by the way, I'm making the lecture notes available to you so you can ask to get them, and the answers to the quiz for people who do care about that are also available to you electronically if you want to download them. So the lectures in PDF form are welcome to have them. I will not go through the detailed derivations pretty much. I'll just give the resulting formulas and discuss their implications, just because we don't have time in this type of form. A lot of the derivations are directly in the notes. You can follow them there for those who are interested in that level of detail. Let's see, anything else? At the end, as it was mentioned, there will be a 30-minute quiz. It's 10 multiple choice questions. There's no hard computations. It's basically on the concepts. I will point out the 4 or 5 things as we go along that show up on the quiz, so you have a heads up that this is what you should be thinking about for those who want to get the credits for the class. Any questions on the overall layout of the class that anybody has? People hear me in the back, by the way. I normally talk loud, so or if they may tail off at the end of the day if my voice fails, but I'll do my best. Okay, my contact information you'll find in the lecture notes. Just a little bit of background about me. You already heard my bio, but just a little bit. So I came to the Jet Propulsion Lab originally in the early 90s, and I came to work on the Magellan radar, which is a radar that mapped the surface of Venus in the early 1990s. And I've maintained a love for Venus, as I'll tell you about throughout my career because of that experience. I then went and worked on the Cassini radar. I helped design the radar for that. And planetary missions are very interesting. They can last decades. And Cassini was one of those missions. So in my early career, I helped design the radar. Then I went away for about 7 years, worked on a bunch of other stuff. And then I came back and helped design all the processing for processing the radar. So, for these long-lived missions that can last basically your entire career. I worked a lot on airborne programs. I've helped work on the AirSAR system, which is one of the early radars that provided a lot of data that a lot of people cut their teeth on in learning radar remote sensing. I was the chief scientist for a dual frequency airborne interferometric radar, the GeoSAR radar, which I helped design so you could actually measure topography beneath the vegetation, which was its main goal. I led the team that designed the processor for SRTM. For those who don't know about that, that was the shuttle radar topography mission. You'll hear more about it during the lecture, which mapped the Earth's topography in a consistent manner between plus or minus 60 degrees for the first time. So it was a major breakthrough, one of the crowning achievements in my career, which I'm very proud of. I've worked on mapping the moon from the Earth using Earth-based radars. You'll hear a little bit about that today too. And so mapping the topography of the South Polar region. I was the principal investigator. I designed the follow-on to the AirSAR, which is the UAVSAR radar, which is an L-band and now P-band and Ka-band interferometric radars, which we use for a lot of our current science collections at the lab and for NASA. I've helped work on the NISAR system. And right now I'm the the project scientist for 2 Venus missions, one by ESA, the European Space Agency, and one by NASA. It's called Envision and Veritas. So I spend most of my time these days working on Venus missions. So you'll see a lot of examples about Venus because that's what I think about these days, a lot of my time. So that's my background. That's where I come from. As with anybody who's been in the business as long as I have, of course, all this material is not stuff that is original to me. I have a lot of collaborators whom I've worked with over the years. 2 in particular that I'll mention is Paul Rosen, who's now the project scientist for NISAR, and Jacob Van Ziel, who unfortunately passed away a couple of years ago, have been key members of collaborations for me over the years. And so I just want to to make those acknowledgments. So this material is not all uniquely mine. And with that, if anybody has any questions, that's fine. If not, we'll go ahead and we'll kick off the meeting. So I hope you don't mind. I will move around a bit during the lecture. First of all, it keeps me awake and hopefully keeps you awake trying to follow where I'm at any one time. The other thing is I will ask questions. They're not rhetorical. I will expect the class to try to answer. It's another way to ensure you're awake and listening and giving me some idea that you're understanding the material as we go along. So I will expect that from you. All right. So with that, let's go ahead and get started on the class and try to make sure we get to our break. Give me a notice if I try to go past the break at 10:20. All right, so remote sensing can be either active or passive. And so most of today's class, I'm going to be talking about active sensors. So passive sensors receive radiation that's naturally emitted from the surface. So that's what a microwave radiometer would do, and those are used for soil moisture sensing and a number of other applications. I'm not going to discuss those at all. Active sensors apply their own illumination, and then they receive reflected echoes from that supplied illumination. And that's going to be the radars, and I'm going to be talking mainly about a particular class of radar, which I'll talk a little bit later on. So radars are sensors that transmit microwave radiation. So that's a particular part of the electromagnetic spectrum, which spans everything from X-rays to infrared radiation. So and basically it's different frequencies or different wavelengths of light that are going on. And the microwave region basically occupies a region from about a centimeter to a meter. It can be a little bit broader than that, but that's for today, that will suffice for us. So we'll be thinking about wavelengths in that particular range. And wavelength is important, as we'll learn, because the interaction with the surface very much is wavelength dependent. So whether you're an optical wavelength, the micron level, or you're a microwave, you're sensitive to things that are at that wavelength structure that you're looking at. And that's why things look very different at different wavelengths. And so wavelength selection is going to be very important and very much dependent upon the physical application that you're going to be interested in looking at. Radar remote sensing can be applied on both airborne and spaceborne platforms, and I will show you examples of data that has been collected from both types of platforms. They both have advantages and disadvantages dependent on what you're trying to do. For instance, spaceborne sensors have the advantage that they have global reach. You don't need permission to overfly areas in the world. Some countries are more sensitive than others about flying over them. But with a spaceborne sensor, you can acquire data on a global basis. Airborne sensors have the advantage of being lower cost sensors, much lower cost generally to develop. And they have the flexibility of flying exactly when you want. They do not have to follow the laws of orbital mechanics. And for those of you who don't know, spacecraft don't behave like they do on Star Trek or Star Wars. They don't go anywhere flying around wherever they want to be. They actually follow very specific paths that's related to the laws of gravity, and they're much more restricted in terms of what they can do compared to an airborne platform. Okay, so radar has some very unique features that make it the sensor of choice for many particular applications. So radar operates day or night. So it can penetrate cloud cover and it works at night. And because it's an active sensor, it supplies its own illumination. And that can be very valuable for a lot of applications. Radar can operate in all weather conditions. Again, how well it works in different weather conditions depends upon the wavelength. Longer wavelengths, generally speaking, are less sensitive to weather than the shorter wavelengths. So generally speaking, the radars that are used for remote sensing are, to a large extent, weather independent. They can acquire good data independent of that. This is a key thing, and this might show up on your quiz, so you might want to remember this. The resolution for synthetic aperture radar is independent of range. So the two-dimensional resolution of what you're going to see on the ground does not depend how far away you're operating. That's very different from an optical system. For an optical system, your resolution depends upon your range times the angular resolution of your sensor that you're using. So range times angle will give you the spatial resolution. That is not true for synthetic aperture radar in particular. The resolution is independent of the range, and we'll tell you what the resolution does depend on as we move a little bit forward. And then, as I mentioned a little bit earlier, the different wavelengths interact with the surface differently. So different applications can be addressed using different wavelength radars. And these measurements, many of them are not possible with any kind of optical instrument. So that's unique to the radar sensing environments. That's why you want to use a radar. Questions so far? Yes.
So you talk about the weather impact on the signal, radar signal. So do you have idea which is the frequency more impacted than the others?
Yes, so the higher the frequency, the more impact of the weather. In fact, some radars are designed specifically for looking at the weather. Typically, they're very high frequency, like 95, 96 gigahertz or 240 gigahertz. So they're very short wavelength, very long, because then they're sensitive to the small particulates that are involved in, the precipitation droplets, et cetera, that are involved in the upper atmosphere. However, even at X-band, which is a 3 centimeter wavelength, which will be one of the wavelengths that we'll talk a lot about for the radar remote sensing, that can be sensitive to the weather under certain conditions. So it's not that it's completely sensitive, but it's much less sensitive than a lot of other sensors. So, and in the longer wavelengths, you practically can't ever tell, even you can't see anything from the weather itself. It's an impact on the surface, yes, but not from actually propagating.
Yeah, for example, for the case of the rainfall, so for example, for the L band, the rainfall is a little impact. But is it more significant for the X band? How about for C band? Because I'm working on C band Sentinel-1 sometimes. Yeah, so I would let you know.
Yeah, so you will find examples in the literature of, for instance, rain cloud impact on C band or X band data. But these are, those are pretty significant amounts of precipitation when they start to actually show rain cloud signatures in the data. But the cloud itself is usually not impacting data at all. Okay. Do I see a hand up over here? Yes.
Yes. So one doesn't have to make any correction if they're doing both day and night together.
Typically, day and night has no impact on the radars that we're going to be talking about. So there's no diurnal correction that needs to be made to radar data, generally speaking. Is that your question?
Yes. Thank you.
Okay. So the type of radar I'm going to mostly concentrate upon is synthetic aperture radar. And I will talk about it almost all the time, although I think I have a little bit of introduction to more other types of radar in a little bit. So synthetic aperture radar was developed in the 1950s, a long time ago, especially for most of the people in this room. And what it was designed for was to overcome the limitation of resolution in the along track or azimuth direction. So a platform will be flying along, and basically the world to a radar gets divided up into two directions. The distance from the radar, which is called the range or cross-track direction, and then the along track direction, the direction the radar is moving. And basically, by using and combining data in a particular mathematical way from multiple pulses in the along track direction, it's possible to improve the resolution than you would normally expect from a given physically sized antenna on that platform. And that's synthetic aperture radar. We'll talk more about that later on. And so what this will allow you to do is this will allow you to get meter or even sub-meter class resolution operating from space with synthetic aperture radar. As I mentioned, the range and the along track resolution is independent of range in a particular type of synthetic aperture radar. So you can make a very, very fine resolution from very large distance. For instance, I map the moon at 4-meter resolution from an Earth-based radar. So that's a distance of 378,000 kilometers, and you can get 4-meter resolution. Interesting exercise for those of you who know about optical systems. How big an optical lens would you need in order to get that kind of resolution? The answer is it's way bigger than any system that's ever been built. So that's an example of what you can get away with radar systems. Okay, so types of radars. So I will talk very briefly about the different types of radars. These are all active sensors of one form or another, and they're all designed to do different things. I will concentrate almost exclusively, as I said, on this last class of radar, again, because the radar class is short and we have to pick and choose our topics. But a radar altimeter is an altimeter that basically looks straight down and is designed to measure the surface height. It could be the surface height of the ocean, or it could be the surface height of land. So, and basically radars, as we'll learn in a second, are just fancy clocks. They're designed to measure how much time it takes between the transmit time and the time an echo comes back. And from that, if you know how high your platform is flying, you can work out the height of the surface. And there's an example of a topographic map made of the surface of Venus by the Magellan radar, which is my first radar that I worked on at JPL, using radar altimetry. Scatterometers are interested in a different aspect of what you can get from a radar signal. And that is how strong the signal is, what the magnitude of the signal is that's reflected from the surface. And if you use that over the ocean, for instance, you can measure quantities like wind speed or soil moisture, for instance. So this is an example of a wind field that's measured with a scatterometer over the ocean. So it measures how fast the wind is moving over the surface. Another type of radar is called a sounder, and it's designed to penetrate deep into the surface. So it looks down like an altimeter, but instead of trying to measure just the very top, it tries to measure and penetrate deep into the surface and measure what's going on. And depending on the wavelength that you're using and what you're trying to look at, you can penetrate anywhere from tens of meters to hundreds of meters or even kilometers. And this is an example of a radar operating in Mars called the Sherrard radar, and it was able to make a map, I think it's just like 2 or 3 kilometers of the ice cap of Mars. And you can see the different layering over time in the various ice caps. So you get some idea of the geophysical processes and the layering that went on over geologic time by looking at a sounder. And lastly, as I mentioned, there's synthetic aperture radars. They're used a lot around the Earth and around planets. And this is an example of the Cassini radar measuring lakes on the surface of Titan. And they're not water lakes. They happen to be lakes of natural gas or methane that are on the surface. It's actually very cold here. We'll talk more about that in one of my examples later on. Okay, polarimetric radars, they actually use the fact that light's polarized. And I won't be talking very much about polarimetric radars again, just because of the lack of time, but they're also very interesting. And they were actually collect data from multiple polarizations. And polarizations basically is electromagnetic waves, which are what our microwaves are, as we'll find out, are a combination of both an electric and a magnetic field. And polarization just means the direction of the electric field. That's all it is. And but it turns out that the scattering from the surface depends upon the orientation of the electric field. You learn different things by looking at that. And this is a color-coded image from the different polarizations in, I think, Death Valley, California. And the different colors, which represent different polarizations, mean different things. So you can learn stuff by doing that. Radar stereo is using 2 observations. And it's basically the old adage, 2 is better than 1. Well, what happens is if you have observations from 2 different vantages, not only can you learn about the 2-dimensional mapping, you can learn about the 3-dimensional mapping. You can recover 3-dimensional information like topographic maps using radar stereo. Now, radar stereo has been used on Venus. It's also been used on Titan with Cassini. And it can be useful to do, but there's a better way, generally speaking, to make topographic maps with radar when you have 2 observations. That's interferometry, radar interferometry. And that's been used to map the Earth, SRTM, TandemX, et cetera. I've made very accurate topographic maps of the Earth's surface. And one of the Venus missions that I've been working on is going to use radar interferometry to make a very accurate topographic map of Venus, for instance. And then there's radar interferometry for deformation. And this is one of the really cool things that really got its kickoff in the early 90s, which I'll mention later on. And what this allows you to do is to measure the deformation of the surface at centimeter and even millimeter scale. So you can tell the surface has been deforming at the millimeter scale from a spaceborne or an airborne platform. And why is that so cool? Well, basically, you can think of deformation mapping as basically giving you an X-ray about what's happening at depth. So it's like getting a bruise on your skin. You know there's something going on underneath the skin, but you want to be able to see exactly what that pathology was that caused that. Well, by looking at what we call the fringes, or the amount of deformation, that pattern on the surface, and using models, we can be figuring out what's happening kilometers beneath the surface. We can figure out where, for instance, the magma source for a volcano is, or where the fault source is for an earthquake. So deformation interferometry has changed geophysical sciences dramatically over the last 4 decades. Brief history. Well, the first radio waves that were ever reflected and detected by metal objects that occurred in the late 1800s. 1951, Carl Wiley, that's where the first idea of the synthetic aperture radar came up. So I mentioned it was in the early 50s. University of Illinois demonstrates the beam sharpening concept. University of Michigan, I remember somebody mentioned they were there from there. SAR imagery was made using what's called an optical correlator. This is something that no one in this room would ever think about because of how well computers work these days. But in the olden days, when computers could not work fast enough, we actually used lenses to focus imagery. So that's how they did it. The first spaceborne SAR turned out to happen in 1964, but no one knew about it until the late 2000s, 2010 or 2015, something like that, when this program was declassified. First real-time image making was in the late 60s. The first civilian spaceborne SAR, and it wasn't thought to be the first spaceborne SAR for a long time until this was declassified, was a radar built by JPL in the 1970s called CSAT, which was designed, as you guys guessed, for imaging the ocean, but it also imaged a lot of data over land. And the data that was processed from this was basically the data that motivated all the family of spaceborne SARs that are operating today, and there's a ton of them. The shuttle radar missions operated starting in the 80s, and they've demonstrated some of the spaceborne imaging techniques and polarimetry. NASA JPL started the AirSAR system, and as I said, for a long time, this was the most publicly available SAR data where a lot of people cut their teeth on learning about radar. Magellan SAR images of Venus, that's how I got involved with synthetic aperture radar. And then starting in the early 90s, that was when there was an explosion of radars that started to collect data in a systematic observing fashion for the Earth. There's the ERS in the early 90s, Japanese system in 92, Canadian radar in 1994, all operating at different bands. CERC in 1994 did a 3.3 frequency mission. 2000 was SRTM, which made global topography. 2004, Cassini. And now, it used to be I could count on one hand all the spaceborne radars that ever flew. Now there's probably 30 of them in space right now. So there's been an explosion of synthetic aperture radar. So I'm not even going to try to mention them all. But there's lots. This is the imagery of the first spaceborne SAR. It was basically they modified an airborne radar that flew on an F-4 reconnaissance jet, and they turned it into a spaceborne platform. The data was collected in space. It was parachuted to the Earth in an optical container, processed using optical processors on the ground, and that's the image that they were able to obtain. And like I said, no one knew about that until it was declassified. So pretty cool. All right, so let's start talking a little bit about the specifics of radar. Any questions, by the way, on the history or the development of synthetic aperture radars? Okay, so radar is an acronym, stands for radio detection and ranging. So that's what it stands for. So basically, what you're going to do is you're going to transmit some form of electromagnetic radiation, and you're going to time how long it takes from the time you transmit it to the times it comes back. So that's what I'm saying. Radar is just a fancy clock. It's designed to measure time. And what do we know about microwaves? They propagate at what? What speed?
Speed of light.
Speed of light. Speed of light is what?
299.792458 meters per second.
Correct.
In that.
And that's right. And it's a number everybody should memorize and know off the top of their head. So, so that is what radars do. The strength of the signal, the echo, contains information about the surface it's reflecting from. So that's the detection part. There are many variety of applications. We're going to hit some of them as we go along, but I won't hit all of them as we go along. I'll basically probably concentrate a lot on the things that I know about the most. As I mentioned, electromagnetic waves propagate at the speed of light. And because radar is not angle-based, it's time-based. That has a lot of implications about how imagery is formed and some of the issues with that. So for instance, if I emit an electromagnetic signal here, it's going to propagate out. And what it would want to do is it would image things on both sides of the aircraft simultaneously at the same distance. So if I'm flying along like this, happily going along, and I emit a signal, it would go out and it would propagate and it would hit something on the left side and the right side of the aircraft and come back at the exact same time. Can anybody see a problem with that?
The airplane will be moving, so it will not be at the same position.
No, that's not the issue that I'm concerned about. What's the big problem with this? Suppose you're trying to make an image. Yes.
Cancel what?
What?
Cancel what?
Don't cancel, but you get this. You get things back on both the left and the right.
So you don't know which one is coming from where.
Yeah, exactly. So here I am. I'm flying along. Let's suppose I'm looking at the ocean on this side and the city of Los Angeles on this side. All the echoes are coming back together, and they're all mixed together. Well, what am I going to see? I'm going to see a mixture of ocean and of a city. So that's why synthetic aperture radars don't look straight down, because you get this ambiguity of where's the signal coming from? Is it coming from the left or to the right? So when you look at synthetic aperture radars, instead of like optical images, which normally look straight down, we're going to look off to the side, either to the left or to the right, depending on what we're trying to image. And that's the reason why, because things in time will come back at exactly the same time. So, as I said, what's going to happen for a radar, we're going to emit a signal of a particular wavelength, and it will propagate down to the ground, and I will be recording someplace my clock as I go along. It will go down, it will eventually hit the surface, and then it will reflect and come back. So notice what I'm going to be measuring is the round trip time, the time it takes to go there and back, which means that's going to be 2 times the distance. So you're often going to see this factor of 2 floating around. That factor of 2 comes from the fact that my time is measuring the 2-way propagation, and I usually want to know the 1-way distance, okay? So you'll see factors of 2 popping up all over the place, and that's the reason why. And what I'm going to get back from the pixel here is basically something that, how many people remember their complex numbers? Hopefully most of you. So most of you are graduate students. Well, complex number, remember, has 2 components to it, a magnitude and a phase. Radar measures a complex signal. It doesn't measure just a reflected number. It measures 2 quantities at the same time, as we'll learn. So it's going to measure the strength of the reflected signal, which is going to be the magnitude of it. But it's also going to measure something that's called the phase, which encodes sub-wavelength information in that particular quantity. Now, as we'll learn, when you make one SAR image, that phase is completely random from pixel to pixel, and you can't learn anything from it. So you need the magic decoder ring in order to learn information from the phase. And we're going to learn what the decoder is as we go along. I have a number of problems interspersed throughout, which I will skip over. So an imaging radar, as I mentioned, will look off to the side, and it will want to illuminate a particular part of the ground. And we're going to learn how we control where we illuminate. That's going to be related to the antenna. So the antenna turns out to be one of the most important aspects of a radar. Yes?
So when it hits the ground, will the phase shift?
The phase has 2 components. One is related to the round trip distance. And another part is related to what's on the ground. And wait till later, and I will answer that question for you. Any other questions? So I'm going to eliminate an area. That'll be the swath width, the cross-track direction, the range direction. As I mentioned before, the direction that we're flying or along will be the along track or azimuth direction. And what the radar is going to record the voltage of the echo strength that's coming back as a function of time over the swath. So that's what I get. So that's what the radar is measuring. So there's a number of angles that are going to come up in our discussions. Two of them are really important, and I want to concentrate on those. So here we have a radar operating at a height of HP above the Earth's surface of the planet or the Earth. RCB here will be the radius of the body, radius of the Earth, in this case, say. The angle from nadir is the direction pointing straight down from you. Okay, so nadir means the direction pointing straight down from where a platform is. The angle from nadir to the line of sight from the platform to a point on the ground, that angle is called the look angle. It's not very imaginative, but it's very descriptive. So here I am, I'm a radar flying along, I'm looking at your phone right there, that angle from me to that my arm pointing to your phone, that's the look angle to your phone. So there's another angle that's important, it's the so-called incidence angle. And that's the angle from this line of sight to the normal to the surface. So that's normal means perpendicular to the surface. So there's the local surface here, there's the perpendicular, and the angle from there to the line of sight is the incidence angle. Now for a flat Earth, if you're not on a curved Earth, the incidence angle and the look angle would be the same. But generally speaking, when you're on a curved planet, there's a bit of a difference. How big a difference depends upon the radius of the planet and how high you're flying. So for typical Earth-based radars, it's somewhere between 4 and 6 degrees. For planetary radars, where especially when you're imaging small bodies from high altitudes, it can be much larger. So it all depends.
Excuse me.
Sorry, question?
The previous slide, I have.
Previous slide. This one.
Why there is a voltage fluctuation with time in this case?
So remember what radar does. Radar is, an echo is coming down, it's hitting the surface at a particular time, say here, and then it's recording the amount of signals it's reflecting back. And as I move across the swath, the range is also increasing, so time is also getting larger. And so the signal that I'm getting back as a function of time is going to change as I walk across the swath. Did that answer your question? So then you can have formulas that relate the range and the look angle to each other. So this is the formula for the look angle. This just uses the law of cosines, by the way. Oh, and by the way, in the notes, if you get them, I have a mathematical review at the end, which goes over all the math that you might want to have a remote sensing: trigonometry, logarithms, dBs, linear algebra, blah, 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 et cetera. All of that's in the back for those of you who might have forgotten it. And complex numbers. So this is the law of cosines, which shows you how to get the angle from the range, the radius, and the height of the platform. Or if you know the angle, then of course you can find the range and the range and the radius of the planet and the height of the platform. In the flat Earth case, then the formulas are much simpler. Then you can just use your right triangle trigonometry. And this is an example of a computation for a Venus-based radar, where for a look angle of 30 degrees from a platform operating at a height of 250 kilometers, for instance, that would give you a range of 250 kilometers, thereabouts. And if you know the range, you can work out what the look angle is. Yeah, but there's the arithmetic for doing that. You can also work out what the swath width is on the planet, and in terms of knowing that the angles from what's called the central angle, the angle from the center of the planet from the nadir over to for the swath width, and you compute that from the law of sines. So I won't go through that formula, and then you can get it out, and the formula again becomes simpler for a flat Earth. And theta BW here represents the beam width of the radar antenna, which we'll get to in a second. okay? And how big a swath that you're going to image can be anywhere from hundreds of kilometers to tens of kilometers to tens of meters. It all depends on what altitude you're operating at and what platform you're flying on. So swaths will vary widely depending upon your application. As I mentioned, the incidence and look angle are related to each other, and you can use the law signs to get the relationship between beta and the incidence angle. And this is the formula here. So the sine of the incidence angle is related to the sine of the look angle, and the ratio is R sub E plus HP over R sub E. So the first thing you notice is as the radius of the Earth goes to infinity, so that means we're getting closer to a flat Earth, then this number would go to 1. And as I said before, the incidence angle does equal to the look angle. So a flat Earth, the two things are identical to each other. But it also tells you this number is always bigger than this number, right? So this number is always bigger than 1. So that means the sine of the incidence angle is always bigger than the sine of the look angle, which means what? That the incidence angle is always bigger or smaller than the look angle? Bigger, that's right. So the incidence angle is always larger than the look angle, okay? So if you see something where this is when there's no surface slope. So you can always help cross-check yourself by remembering that. Okay, and then here's another example of computations. Okay. So any questions so far? So that's the basic geometry and all that, all the formulas relating that are up at the very beginning of the notes. So as I mentioned before, radar is going to use microwaves. And microwaves are a part of the electromagnetic spectrum. So the electromagnetic spectrum spans a wide range of wavelengths or frequency. So you can think about it either way. And the relationship between wavelength and frequency is related by the speed of light for microwaves or electromagnetic waves in general. So I typically like to think in terms of wavelength. Some of you like to think in terms of frequency. You can go back and forth between the two. I'll try. If you ask me, I will mention them. But so here's the wavelength. So here's the microwave region that I mentioned, basically from a centimeter to a meter. And where we are over here, where our eyes work, is basically around 1 micron. Okay. So the wavelength that we're sensing with our eyes is very, very small. Okay. And so the wavelengths that we're looking at are typically 100,000 times to 1,000,000 times larger than the wavelength we use for eyes. And that's why the world looks very different at radar compared to an optical system, because the wavelengths are so different. And electromagnetic waves interact with things that are on the scale of the wavelength. So we expect there to be different things. So here are the wavelengths and corresponding frequencies. So frequencies basically up to 40,000 megahertz down to the 300 to 900 range. And then wavelengths from a little less than a centimeter up to about a meter. Now, if that weren't complicated enough, of course, we have to add one additional layer of complication. Associated to these frequency ranges, there are what are called bands, naming conventions for the different bands. And there's no logic to how they were named because they were designed to be illogical in the first place. It came about in World War II, and this was a way of encoding secretly the wavelengths for radars, which were very, very secret. And that's so they could send them in communications without people knowing what they were talking about. So, and of course, all the people that worked on radars during World War II, they're the ones that went over and started developing the first civilian radars. What nomenclature did they use? Well, they used the nomenclature they worked on when they were in the military. And so it's stuck, and it's to this day. So these various letter bands are there, and we still talk about them today. I will probably be mentioning mostly just 3 bands during this course, maybe 4 bands every now and then. So there's X band, which is a 3 centimeter small wavelength. C band, which is a little bit larger, around 5 or 6 centimeters. L band, which is around 24 centimeters. And occasionally I might mention P-band, which is around a meter, a little bit less, or a little bit less. So that's where those names come from. I will try to mention both as we go along because it's hard to memorize all that stuff in one day. But that's where the band names came from. And so don't blame me, I had nothing to do with it. All right. Now we'd already talked about this geometry here for synthetic aperture radar. We now want to get a little bit more specific about what we're actually seeing on the ground here. So we're going to talk about it very briefly in a minute, is a little bit about antennas. So synthetic aperture, you might think that antenna is important because it's involved in aperture, and indeed it is. So, but there's one key thing about the beam width of a radar that you need to know. And this is an important thing, and that is that the beam width is related to the wavelength and the size of the antenna. So how wide that you're illuminating in angle depends upon the wavelength and the size of the antenna. And this is true for an optical system too, how big you're looking at it. And so what does that mean then? So the smaller the wavelength, the smaller the angle, the smaller the beam, and the larger the antenna, the smaller the beam. So small antenna, fat beam, big antenna, narrow beam. Got it, everybody? Yes.
So sometimes, like for the radars, but like spaceborne radars have like 2 wings. So does it account for like both the wings, or is it just?
So usually when there's, sometimes I don't know which radar you're talking about. But
in general?
Well, general is quote unquote, it depends. So usually when there's 2 antennas,
Yeah.
they're either doing one of 2 things. They're both looking to the same direction and they're trying to measure the same swath so that they can do something like interferometry or stereo or something like that. Or they're looking at opposite sides so that they can increase the swath width that they're looking at. So it depends on what system that you're
That's
speaking.
like one wing is one.
What?
Sort of, so one side is one antenna, but like they don't constitute to become like one big thing.
There are ways to combine data for different antennas to make a bigger antenna. I'm not going to talk about that in this class because that's really much more complicated game. And the issues about combining data from different antennas have a lot of really interesting mathematical implications that restrict what you can get from it. It's too far afield for us today. So I'm not going to be talking about that. All right? And what does that mean then for about how much swath width that you can measure on the ground? But remember, if you multiply range times angle, that tells you the distance that you're looking at. So the distance that you can get in the along track directions, or how fat the beam is this way, depends on how long the antenna is in the along track direction, L-as, and then the range and the wavelength. And how wide your swath is in the cross track direction depends on how fat your antenna is in the direction perpendicular to the flight path, and that's L sub rho, and so that will give you your swath width on the ground in that direction. So if you want to have a fat swath width, you have to have a narrower antenna. And if you want to get a narrow swath width, typically you would want a larger antenna. Now, what we're going to learn when we talk about the radar equation, nothing's for free and everything's a trade if it's floating around. So when you want one good thing, usually that comes at the expense of getting a bad thing. And so every single time you're doing something, something else is happening at the same time. And so you have to keep your eye on multiple things at once. You don't just get to change one thing usually and have only that thing get affected. And that's going to be a theme that we have to be very careful of when we're thinking about radar systems. So synthetic aperture radar basically is I'm going to fly along and I'm going to emit a pulse every time I come along. And eventually I'm going to hit my object. And I'm going to record data for each one of the pulses as I fly through and I'm illuminating from my beam. And then what I'm going to do is I'm going to combine the data from all those pulses. that were there when I was in the beam. And now, instead of having antenna that's basically the size of whatever I was flying with, I'm going to have a synthetic antenna that's big as as the distance of when I was inside, when I was able to collect data over that point. So it becomes much larger. It can be many kilometers in size now. So what's the price I have to pay for that? Well, now I have to do a very complicated mathematical procedure for combining the data from all those pulses in order to make that synthetic aperture. And what I get in return for my effort is I get much better azimuth resolution that's commensurate with just how big that antenna is in azimuth. Okay, so that's the idea of synthetic aperture radar. Combining data from multiple pulses to synthesize or make a long track antenna to improve my resolution.
So this is one point only they are imaging at different.
Sorry. So for each time I fly along, I'm going to emit a pulse and record the echo as I'm coming down. And as I get into the beam, there's one pulse, there's another pulse, and I record the signal for each one of those as I go along. And as I keep flying through, eventually I will get into the beam, and then I exit the beam. And now that's the total number of signals or the number of pulses that I collected while I was in the beam. Does that answer your question? Yes.
By beam, you mean the object.
Beam, I mean the antenna footprint over here. I'm illuminating the ground with the radar beam, which is from a certain size antenna. And so that's where I'm looking at. So think of a flashlight. I point a flashlight at the ground, it makes a spot, right, on the ground. That's the beam footprint. And if I move my flashlight along, then my beam is moving with me. So sometimes I might see something on the ground and sometimes not. It all depends on where I'm pointing my flashlight, right? You don't look happy, so I don't know your understanding.
I got that. So beam means the whole area that you are
The
looking
beam footprint is the whole area. The beam is this illuminated angular region where I can get signal from. The footprint is where I'm hitting it, where it intersects on the ground. So it's just like when I look at a flashlight, I see the beam going down, and I see it's been in space, and then it will make a footprint on the ground.
So the beam hits the ground, returns back. So the beam hits the ground.
The beam doesn't. Well, the beam is basically where I'm illuminating. The signal propagates down and hits the surface and then comes back. And
the sensor that is there, it is moving and taking the.
So what's happening is, so let me try this. My phone is the antenna. I'm looking off to the side. If I turn it on, it will start to illuminate the ground, okay? So when I do that, it's going to illuminate the ground, and then I'm going to send out a signal, and then it's going to come back, and I'm going to record it. Then I'm going to move over. I'm going to send another signal down. I'm going to record it, and it will come back. And so that'll be what the radar's doing. That make it any clearer? Yes.
So for the fixed height of the platform, the size of the synthetic aperture radar depends on the flying speed.
The speed doesn't really play a role in terms of the resolution. So let me give
Not the resolution, the size of the antenna.
the speed doesn't play a role either. The speed will determine how long it takes to walk through the beam. So the beam's a certain angle. If I fly really fast, I'm going to go through really fast. And if I fly really slow, it'll take a long time.
But the signal will, the signal speed is fixed, right?
The echo's coming back at the speed of light.
Yeah.
So
So there's just a limited amount of signal that you can get if you're flying at a certain speed.
no.
No?
I'm not sure I understood what you're saying, and okay. You may be right, you may be wrong, but I'm misinterpreting. So the speed of light is very, very fast compared to the speed of a platform. We're not flying at relativistic speed for any radar in this class. So when the radar emits a signal, it goes down and back and it comes back in microseconds, really, really fast. Now, it's true the platform continues to move a little bit as the echo goes there and back. So even if you're flying at 7 kilometers per second, like a typical airborne platform, in microseconds, it doesn't move that much. It just moves a little bit. And it's usually way less than the size of the antenna even. So the echo will come back. Then I will wait, this time typically milliseconds, before I do my next pulse. Now the echo will go down and come back in microseconds. And then I fly along. Did that help at all?
So there is a possibility of the same point being mapped twice as we.
The same point will be made mapped many times, hopefully, because I want it to be in the beam for many, many pulses. Otherwise, I can't combine the signals together to do synthetic aperture. Yes, that would defeat the purpose if it was only in one pulse. There's no synthetic aperture for it.
How much is that number? Like how many images do you need to?
How many pulses?
Yes.
It can be anywhere from tens to thousands, depending upon the system. There's no one answer that I can give. Yes.
So the pulses have the same frequency or different frequency in this case?
So they all typically, you want them to have the same wavelength, otherwise you can't combine them together. There's a little bit of a nuance to that, but let me get to that a little bit later on. Okay, so let's see what time is it. Okay. So there are many ways to make a SAR. Excuse me. There are many ways to make a SAR or a radar. And I can't go through all of them. But a basic SAR system consists of the following things that you need. One thing, you need a way to generate and receive microwave radiation. So that's going to be the transmit system and an antenna. You need a means of receiving and recording the reflected signal. You can't record it, it's like you didn't do it. So you need to make a record of what you're doing. And then you need a way to command and control what the radar is doing. How fast do I pulse? When do I record data, et cetera? So some sort of brains. And then to form imagery, you need some other additional ingredients. Basically, you have to have good phase coherence. I'm not going to talk about that in a lot of detail from pulse to pulse. So that's what's called a stable local oscillator, meaning that you basically can tell how good your wavelength, that you have the same wavelength to very high precision from pulse to pulse. You need to know, and this is a key thing, in order to do this mathematical combining of all the pulses, you have to know where the antenna was every time you pulse that radar. So you need to know the position of the antenna from pulse to pulse. And how well do you have to know it? A fraction of a wavelength. So this imposes some metrology. Now for baseborne systems, we're really lucky. Satellites fly very smooth paths in space because there's no atmosphere to bump them around. Airborne platforms, life is a lot harder. So I'll leave it at that. And then you need some way, a mathematical way of combining the imagery. You need an algorithm and a computer these days in order to actually combine the data together. So this is a block diagram of a typical radar. So you have the radar controller, the brains, says, I want to collect data now. And that will go to the control and timing unit that says, okay, how fast do I want to pulse the radar? And it may be kilohertz, pulse every thousandth of a second or whatever. This will use a clock, and you have to keep everything in sync. So you're going to use a stalo as a frequency reference, sort of like a crystal, and it's going to give you a good clock, a way of keeping track of all the relative timing in the radar. As we'll learn later on, we're going to emit a pulse, and we're going to use a particular waveform, and I'll talk about that later on. It needs to be converted to the right frequency for the transmitter, and then it gets sent to the antenna where it propagates out the front end. Then it will hit something, hopefully, and the echo will come back, and then it will come into the antenna. I told you we needed to know where the antenna is, so we'll have some sort of metrology, like a GPS and other things. We'll take the signal that we get back, we'll typically turn it into a lower frequency, It will go into the receiver where we'll turn it from a voltage into a number, an analog to digital converter. So we can use it in a computer. And then we'll put it on to some sort of storage device or send it to a processor to turn it into an image. So that's the basic aspects of a radar. I'm going to go through a really quick tour. So first of all, remember, I'm a mathematician. I know nothing about radar hardware, except enough to annoy radar engineers not ad infinitum. But so I can't really answer any IEEE or any electrical engineering type questions. So I do have a physics degree, but I didn't pay attention to any of that device. Okay. So synthetic aperture radar, we've learned what it does. And we really, as I mentioned, I'm going to talk a lot more about antennas in a second. But it's basically the antenna that drives a large aspect of the system design. So what is it about antennas? Well, I already told you the most basic thing and the most important thing, and that is that the width of the antenna, the angular width, is proportional to the wavelength and proportional to the size. I often use in this course K equal 1, but K doesn't equal 1 for all radars. It varies from like 0.7 up to 1.3 or 4, something like that. But for this class, 1 is a perfectly good number to use for that. Now, you notice this 3 dB thing. What's that about? Well, an antenna does not just illuminate from angle A to angle B and nothing else. It would be wonderful if that were the case, but that's not how real antennas work. So a real antenna is going to illuminate from the desired angle range I want if I've designed it correctly, but it spills energy all over the place, not just where you want it, unfortunately. So the shape of a beam typically looks like this. So it'll have some shape, and the width here at the point where you get to half the power, which is the 3 dB point. So radar engineers use logarithms, so 10 times the log of a number. And 3 dB, as it turns out, is basically the log of 1/2. 10 times the log of 1/2. And that's log base 10, not the natural logarithm. And so this width here is measured at the 3 dB point. That's just the convention. And so this width here is at the 3 dB point. This area here where you want to get most of the energy, that's called the main lobe. Okay. For obvious reasons, it's the main part of what you're interested in. And you know that you're measuring this angle here called the 3 dB width, but there's still data coming in from the main lobe further and further down. All these little things off to the side, they're called the side lobes, and they spread out in all angles. Hopefully, they drop off as you move away from there. And you can by how you design the antenna determines what the side lobes look like, what the structure is of them, how fast they drop off and stuff. The peak gain, how much signal you're getting back at the peak of your main lobe, depends upon your wavelength, inversely proportional to the wavelength squared, and the size, the area of your antenna. So this is called the gain. So this is how much magnification you're going to get back of the signals coming back at that peak point in the antenna. The bigger the gain, the better the antenna is. But now comes some of the trades, the games you have to play. So the bigger the area of the antenna, the bigger the gain, the more the signal is you can get back. That sounds good, right? Everybody's really happy. I want to make a really big antenna. So, but there's a few things that are going on here. Remember what I said, the angular width determines how much area that you can measure, what your swath width is. So if I want a really strong signal, then that would say I would want to have a very big antenna. But if I have a very big antenna, I'm going to have a very narrow swath. So remember I said there's always this trade? Oh, whoa, wait a second here. So now I have to play a game. I can either have a wide swath or I can have more signals. So somehow I have to balance between the two of those things in order to get the right design for my system. Well, you're saying, oh, well, that's fine, Scott. So you can only make the antenna a certain size in the range direction because I want a certain swath. But why can't I make it really giant in the azimuth direction then? And then that way I can get my gain up and still have my wide swath, right? Everything sounds wonderful. As we'll learn in a second, no, there's another trade to be made there. And so that doesn't work either. So everything's a balancing act with radars. Everything's a balancing act. All right, so what I really care for you to know for today about antennas is small antennas give you wide beams, big antennas give you narrow beams. Beam, how wide it is proportional to the wavelength and proportional to the size of the antenna. And the gain, how strong the signal is, depends upon how big the antenna is and the wavelength. That's it. Yes?
So does it mean that whatever our 3 dB is, that's like the angle we are, that's the basically.
It's the nominal area we wish to be looking at.
Okay, and like if you go beyond it.
We're still going to get signal.
But like it's about 1,000 times smaller than.
Well, it's going to be how much small, it's going to drop off like
Okay.
this. This is telling you at each angle how strong the signal is. It doesn't just instantaneously change. The next angle over is just a little bit lower and so on and so forth. You try to make this drop off as fast as you can so you get the area you want. But there's the laws of Fourier transforms, for those of you who know what Fourier transforms, tells you can't do that infinitely fast unless you have an infinitely long antenna.
So 3 dB is already 1,000 times smaller intensity, right?
No, it's half from the peak,
Oh,
one half. 3 dB is one half, remember? Yes.
Yeah, the rule the small antenna, wide beam, and big antenna, narrow beam apply for on the tip of the antenna or and for on the frequency.
So if you're asking if that's a general rule, yes, it's a general rule. It applies to all antennas at all frequencies. Yes.
Even for the antenna, it's the I would say the length antenna or on the tip of antenna. No,
I don't understand your question.
they are placed on the tip of antenna. It means that for the multi-beam antenna or the of one antenna, because I'm work on a little bit on the antenna design, so I know that for the antenna technology we can reduce significantly the size of antenna, but we can obtain also the
array.
Yeah, array. Yeah.
So there's just a fundamental limit. So there are tricks that people play to try to get more for their dollars, but there's always a price to pay.
Yeah.
So nothing is for free. So sometimes people they try to force to get a narrower beam in a smaller size antenna, but typically what that happens is that means that they get a big problem for far out angles. So they have to pay for high side lobes somewhere. Now, if those high side lobes are someplace it's not unimportant, then that's great, then it works fine. But if they matter, then it's a problem. So nothing is for free. There's always a price to be paid to get a gain. There's the laws of physics are the laws of physics, and they're really very much a pain in the butt. Yes.
So do you always try to make the beam width narrow at the side lobes low? Is that?
If you had a perfect antenna, it would be rectangular in shape and then zero every place else. That would be the perfect antenna. And you can have a perfect antenna if it's infinitely long. But since there are no infinitely long antennas, what you're always trading, you try to get this beam width to be what the angle you want here and to drop off as fast as you can within the main lobe and then have the side lobes drop off quickly. And there are tricks for trying to do that, but there are trades in how well they do and how well they behave. Typically, if you want the side lobes to be down really low, then you have to pay for a broadening of the
So you choose the window accordingly, rectangle.
Yeah, the window and aperturing, yes, which I'll talk about in just a second and show some examples. Yes.
So there is some kind of interference happening, right? So you have like constructive interference.
Yeah, let's not go into that right now. That's a little bit too much. I'm happy to talk with you offline about it. Well, I'll hit the high points when I show the math. 1 second. All right. So everything that you need to know for today is on this page. Everything else I'm going to show you now is just extra credit, just to show you the ideas, but not going to go into the details because it takes too much time. All right, so then you can compute examples of, for instance, X-band, 3 centimeter wavelength, 4 meter sized antenna will give you a beam width of 1/2 degree, for instance. All right. In order to understand the mathematics, and also, which will be very important in interferometry as well, is of making how an antenna beam is formed, you have to understand the concept of phase. And for the purposes of this class, you could think of phase as just another ruler. It's another way of measuring distance. But it's a distance that's measured in units of radians, which are basically boils down to number of wavelengths. So what is the phase? If I have a distance, say delta rho, and I have a wavelength, the wave will go here and there'll be so many wavelengths over that distance. If I take the distance divided by the wavelength, that's just the distance in wavelengths, right? So if I have, for instance, if I have a 3 meter distance and I have a 1 meter wavelength radar, 1 goes into 3 times, so it's 3 wavelengths long. If I have a 1/2 meter and 3 meters, then it's 6 wavelengths long, etc. So distance divided by the wavelengths tells me the number of wavelengths. And how much phase is there in one wave? Well, that'll be 360 degrees or 2 pi radians. I don't do degrees in this class, so for us, we're going to do radians, because radians relate to distance by multiplying by the phase. So phase basically is just another way of measuring distance. Now, the key thing about interferometry, which we'll learn, is that we can measure the phase to a very small fraction of a wavelength, which means we can measure distance very, very well. In antennas, which is what you are getting at, what we need to do is we need to combine signals in such a way that the phase adds up in the right way. If it adds up in the wrong way, so for instance, if they're separated by pi, they're going to cancel each other out and I don't get anything. So the whole trick of antennas and synthetic aperture radars is adding things in the right way in phase so that I can get constructive interference, as you would call it. And I think that gets back to the point you wanted me to make. Okay, I'm going to skip this page here. This is something called the far field. I'm not going to go into it, but basically that tells you how big your antenna can be before you run into some trouble in doing this. So what you're going to do to form an antenna beam is the following. And this is where the gain pattern comes from, that pattern I was showing you before. What you're going to do to get your signal as a function of theta here, how far away you're pointed from the center of the antenna, the boresight angle, is I'm going to add up for each point in the antenna. It turns out that I can have what's called the aperture distribution. I'm going to give the relative strength that I'm going to apply to the signal arriving at that point in the antenna. So for instance, I might have a signal strength of 1 for things that arrive at the middle of the antenna and 1/2 when they arrive at the edges. Or it could be 1 all along the antenna. That would be uniformly weighted. And what I'm going to do is I'm going to add the signals that are coming back in phase. And so what is the phase going to be? Well, it's going to be the distance from a constant range line. So this is a constant distance along the antenna, signals all coming back at the same time. And the phase will be related to the angle times whatever this distance is. And that's going to be this distance dotted into this vector here on the antenna. And if you want to think about it in terms of angles, that'll be sine theta. You can figure out this distance here is L sine theta. And so does everybody know what the exponential notation is for numbers, complex numbers? Who doesn't know? Who needs a reminder about complex numbers? At least one person. One honest person in the room. Okay, so a complex number is equal to a real part X and a complex part Y. So X plus IY. Okay, that's what a complex number is. So it has two parts to it, the real part and the imaginary. It turns out that that's not a very convenient format for us to use for complex numbers. A more convenient format uses the angle, theta, and the distance, r, the magnitude from the origin to the point out there. So we have r and theta for a complex number. Now it turns out that e to the I theta, e is the base of the natural logarithm, 2.71828. I don't remember the decimal places after that. And it turns out that that's equal to cosine theta plus I sine theta. Well, this distance here along this axis here is x cosine theta. And this distance here is r cosine theta. This will be r sine theta. And so we can compactly write a z equal r e to the I theta, which is equal to r cosine theta plus r sine theta, which is equal to x plus IY. Okay? Now, why do I want to write them this way? Because when I multiply complex numbers this way, it's really easy, because what do we have to do? So if I have two complex numbers, r1 e to the I theta 1, and z2 equal r2 e to the I theta 2, then z1 times z2 is equal to, well, you just multiply the guys sitting out front, r1, r2, and what do you do when you multiply? You add the exponents, so I times theta 1 plus theta 2. So when you write complex numbers this way, multiplication becomes trivial. And it has a geometric meaning. You multiply the magnitudes and then you add the angles together. That's the 30-second introduction and overview of complex numbers. All right. And there's a lot more about it in the mathematical review for those who want to go into more detail. So basically, this is just saying you're adding up all those signals in just the right way to form the signal. And that forms that pattern that we showed before. And if you do a uniform weighting across the aperture, you get something called the sync pattern. So this pattern here is called a sync. So you'll hear that oftentimes, which is basically sine x over x. So when you hear that formula or hear about a sync pattern, it's just sine x over x. Okay, I'm going to skip this one. So remember I said if you change the weighting or how you combine them, that can control the side lobes and the main lobes. So this is a typical thing called a cosine and pedestal weighting. It's a temperature weighting. And eta is a parameter that controls it. If eta is equal to 0 or 1, it's uniform. And if it's equal to 0, it's called it's actually hand weighting. There's no ing there. And so you can see what the different patterns look like. So black is uniform. So that's our sine pattern. So this will be our main lobe. And then you can see our side lobes dropping off. But if I go to, say, change the weighting to eta equal to 0, what happens? That's the blue guy. I lose some peak gain. I get a much wider main lobe, but my side lobes drop off much, much faster. So this is a trade that antenna designers play. They go, okay, what do I want to do for this application? Whether it's communications, radar, or whatever, depends on what you're trying to do. And when you design the antenna, you're trying to figure out, well, what main lobe works for me and what side lobes can I live with? And it all depends on what you're trying to do. So, but this is, and it's more complicated than this, but that's the simple story. And I don't have time to go into the math in any more detail today, but that's the general idea of the antenna theory. So I will skip that. And then, of course, our antennas are not one-dimensional, they're two-dimensional, so you have to worry about the two-dimensional pattern. And in some cases, you can pretend it's just a one pattern, an azimuth pattern times a range pattern. That's the separable case, like if you have a rectangular antenna and a nice type of distribution, and things can get more complicated from there. But I will not go into that. All right. So we have 10 more minutes, so that's good. So I can start my next topic. So first of all, are there any questions on antennas before I move on? So remember that there's that one page, which is all I really care about that you need to know. The other stuff was just for the edification. I know there's probably some electrical engineers in the room that wanted to hear a little bit more detail, so that's fine. But you don't have to know it. Okay, so I already brought this up before, but let me do it again. So the synthetic aperture imagery is going to be broken up into two directions. The range direction, basically the time it takes to go from the antenna to a point on the ground. There will be a certain resolution to the radar, which will be called the range resolution, delta rho, in this slide here. And then we're going to have the azimuth direction, and then there'll be a certain pixel size in the azimuth direction. And for each pixel, I'm going to get a signal back, okay? And that signal is going to be a complex number. And there it is, an amplitude, A, and a phase, phi. So there's where that complex notation comes into play. So I'm going to get an amplitude and a phase. So what I want to talk about in this particular section is what contributes to A? How is A determined for a given pixel? And then a little bit about the phase, and we'll get a lot more into that in the interferometry section later. Okay. So we get a magnitude and a phase, we get a complex number for each one of our pixels. Any questions here on the basic? Yes, go ahead.
So in 2D, do we care about the solid angle and not just one sort of line?
So I'm going to cut to the bottom line here. The world is going to be divided by the way we process the data into pixels. And basically and in that processing, it subdivides the energy for you and places it on the ground in bits. So it's already broken up, basically the energy, all the energy that you transmitted is going to spread over the ground. But where it gets concentrated determines from how you process it. And that signal then it will come from this mathematical processing of the data. Yes.
So the radar will measure the distance by calculating the time between the reflection.
Yes.
And the phase of the signal that it received.
And the what?
Phase of the signal that it received.
The field?
Phase.
Phase, yes.
So the azimuth is the phase.
No.
Okay.
Phase will be related to two things. And if you'll wait a little bit, I'll talk about that more, okay?
And the distance is the range.
And the distance is the range.
So what is the azimuth? You will tell later.
That's coming up. I'm going to talk about this phase in more detail and the azimuth in more detail. Right now, I'm just telling you the world, in an image, the world gets broken up into range and azimuth. I haven't told you how yet. So for right now, I waved my magic wand and I divided the world up this way. And you know that somehow the range is related to the time that it takes the signal to come back. That's true. Azimuth is a little bit more complicated. We'll get to that in a second. And the phase is also a little bit more complicated. So we're going to break that up and talk about it in a second. I'm just telling you though that you get a complex number. And that's something that's different from optical imagery. That you get a complex number instead of just a real number. Any other questions? All right. So the magnitude, the A, is the amount of energy reflected by the pixel on the ground to the radar. And it depends on a number of different parameters. And so the good news is and the bad news. The good news is it depends on a number of different parameters. And the bad news is it depends on a number of different parameters. So why is it good news and bad news at the same time? Well, the good news is because it's sensitive to different things. So if you want to measure soil moisture, hey, turns out it's sensitive to soil moisture, so you can measure it. But it's also sensitive to surface roughness. Ooh, that's bad. So So what it happens is that, and this is true of almost all remote sensing, not just radar. When I measure a signal coming from a surface, I'm going to get something often, because I've designed my system that way, that's sensitive to the thing that I care about. For instance, soil moisture. But it will also turn out to be sensitive to things I don't really care about. And that's where the trick of the processing and the manipulation of the data comes in. What I want to do is compensate for what I don't want to leave what I do want. And that's true of much of remote sensing. So I find something that's sensitive to what I want, and then I have to find a way to compensate for the aspects I do not want. Okay? That's the real world. It's the way it works. Okay, the phase is a function of a number of things. It's actually a function of the distance too. Remember, phase is just a ruler, so it's not unexpected. It's going to be related to the distance from the radar to the point on the ground. But it turns out that there are other things that start to complicate. It actually is related to the composition, the way the material that the substance is made of, and how it's mixed within a pixel. And it's related to what's called the elemental scatters, the distance to individual things that contribute the most within that pixel back to the radar. And I'll have a picture of that later on. So this turns out to be a very complicated thing. And this is what I said, you need a magic decoder ring in order to separate things and make use of it. And we'll talk about that in a little bit. And so there's the phase. And this is the things that I was showing you earlier on the blackboard. It's also here in the slide. Questions? All right. What is the magic decoder ring? Well, here's the basic thing, and we'll go into a little bit more detail, particularly about this aspect, not so much the other one. So you can think of the phase as having two components. One, the scattering component. That's related to what's happening within the pixel itself. What is it made of? How is it arranged geometrically within that one little pixel? Okay? So, for instance, let's suppose this tabletop here is my pixel. And there's my phone, and there's my water. And the water will contribute a certain amount of signal back, and then my phone will contribute a different amount of signal back. And they're at different places within the pixel. So the phase will depend upon, and the scattering phase will depend upon how these things are stuck in my pixel and how much relative signal they reflect back. So it's a complicated thing and it varies from pixel to pixel to pixel. The extra part is the geometry part. And that's going to depend upon distance. That's going to be my ruler part of it. Now, if I want to get the scattering part of the phase, this is where radar polarimetry comes into play. Here I'm going to exploit the fact that if I collect data at different polarizations, I can use one polarization as a reference. The geometric part will be the same for all of them, and I can cancel it out. And I can be left finding out something about the scattering information. And that's great. If I want to find about soil moisture, if I want to find about the surface roughness, if I want to find about sea surface salinity, all of those things I can learn more about by using that technique. But let's suppose I don't want the scattering, but I want the geometric information. If I want the geometric information, that's where radar interferometry is going to come into play. So if I want to measure surface topography or surface deformation, I don't care about the scattering. I care about a geometric effect. And that's where I would use this. So the magic decoder thing basically are these two aspects of radar observation, polarimetry and interferometry. And each of them basically does a certain sort of cancellation. One cancels the scattering portion of the phase, and another cancels the geometric portion in order to be able to exploit the data. Okay, so what is polarization? Polarization, as I mentioned, an electromagnetic wave consists of an electric part and a magnetic part. Hey, doesn't take a rocket scientist to figure that one out. And basically the electromagnetic components, the fields, they are perpendicular to the direction of propagation. So the E field and the B field, as they're called, are perpendicular to the direction I'm going in. So if the electromagnetic is pointing this way, the The E field may point this way and then the B field this way. But it turns out the strength of them is changing as a function of time, like this, as I'm propagating along. But more than that, their directions can also be changing too. So they can be rotating as I fly along as well. The direction of the E field is called the polarization. So if it's vertical, it's vertical polarization. If it's horizontal, it's horizontal polarization. If it does something funny, it can the thing that it can really do is it can trace out an ellipse in space. That's the most general thing it can do. So you can get elliptical or circular or other types of polarizations. And why you care about that is because what gets reflected from the surface depends upon the orientation of the electric field. So as it changes, the signal changes back from the surface, and you get different information. And that's why having the different polarizations, if you cancel out the geometric portion, you can start to get different information about what's happening on the surface. How we measure or quantify how much scattering we get back from the surface is often done in terms of a quantity called the radar cross-section. The units of that are area, and it's related to how much signal I'm going to get reflected back from the surface, and it's a quantity that's associated to it. That's not, this is what military radar people think about. They think about the radar cross-section. They care about the radar cross-section of a B-2 aircraft. Small radar cross-sections means you'll get back really small signals. So they want to design an aircraft with a very small radar cross-section. I don't care about that stuff. So what we care about in the remote sensing community is something a little bit different. And what we normally care about is something called the backscatter. And basically what we do is we take a radar cross-section, which is in units of area, and we divide by the area of the pixel. Okay, so we normalize it. So we divide it out, and we're left with something that we call the backscatter. So if we're measuring a surface, say a forest, or I'm measuring a wheat field or something, well, if I want to figure out how much signal I'm going to get back, what I'm going to do is I'm going to take the backscatter, which is an intrinsic property of the type of thing that's doing the scattering. For instance, a tree or a cornfield. I would multiply that by the area of my pixel, and that would tell me how much signal strength I would get back. That's why we normalize it, because we want it to be related to what we're scattering from, not the size of the pixel itself. So we want to get rid of the size and leave something that's intrinsically related to what's scattering off the surface. That's the backscatter. There are different ways of representing backscatter. There's the gamma and the beta. I'm not going to care about all that. We're just going to, for the purposes of this class, everything's just going to be backscatter. And we'll let all the other people pedantically worry about the various other types of normalizations. But for today, I divide by the area of the pixel, and I have something that's related to the material on the surface. And it's exactly 10:20, which means I owe you a break. So I think we have a 20-minute break. So you're welcome to take a break till 10:40. If people have questions that they're too embarrassed to ask, they can ask me during the break, of course. I'm available. So enjoy your break.